2, 1, here we go. All right, so let's look at example 3. For the equation y equals x plus secant of y, find dy dx. Okay, so we're trying to find the slope of the tangent line to this right here. Is it solved for y? It looks like it, right? It's y equals, but is it solved explicitly for y as a function of x? No, it's a function of x and y on the right-hand side. So your first step is, can we solve it for y? Well, that's going to be rather difficult because the one y on the left is already free, and the other y that we're trying to get together is trapped behind a secant, yes? And if I were to try and free the y that's in the angle behind the secant, I would have to take the inverse secant of both sides. I could bring the x across, y minus x, but then the y minus x would be trapped behind an inverse secant. And how would I free it from inside the inverse secant? I would take the secant of both sides. And so freeing one enslaves the other. So I'm not going to be able to solve it for y. Is that strawberry? Because Pop-Tart has a giant lawsuit right now that there's not enough strawberries. What would you say?
It tastes like a lawsuit.
It tastes like a lawsuit. Very nice. Maybe it's a class action. You can get in on it.
Maybe I can.
Yeah. All right. So here's the deal. We still want to know what the derivative function is with respect to x. It's not solved for y. We can't solve it for y. Darn it, we're out of luck. Unless there was a way to take the derivative implicitly. Hey, there is, right? So here we go. Here we go. Now, some people like to rearrange the terms in the beginning. They like to put all the y terms on one side and non-y terms on the other. You can certainly do that. We're going to have to do some algebra anyway on the back end. So my experience kind of tells me that it's not really worth doing, but I'm not going to stop you if you want to do that. I had one girl one year that was adamant about doing that, and I was like, that's fine. I'm not adamant about you not doing it, but every day she told me, I'm going to do that. And I'm like, fine, chill, you know. She's like, I don't care what you say, I'm going to do it. I'm like, I didn't say anything, right? You get students like that every once in a while. You know what I'm talking about? Right. All right. So here we go. D dx colon. What's the derivative of the left side? What's the derivative of y with respect to x? dy dx. Yeah. Don't lose your skills here. Equals. What's the derivative of x, the first term with respect to x? 1, right? Or wink, wink, dx, right? Which is really 1. Okay, boom. Plus secant of blob. Huh? What is the derivative of secant of blob? You had it on the warm-up, right? Secant of blob, tangent of blob. Now, we can pretend that we don't even know what the blob is on the inside. But now we go inside and like, oh, look, there's a y. So chain rule times the derivative of the inside. Well, that's a y. What is the derivative of y with respect to x? dy dx. Yep. It's the chain rule. Okay. The reason we don't have to worry about the chain rule if that were secant of x is because when we would quote unquote do the chain rule, we would get dx dx, which is 1, the identity element of multiplication. Not needed. So here's your checkpoint for taking the derivative. The derivative is over, but check yourself here. How many y's do we have in the original equation? There's 2. Guess how many dy dx's you should have in your derivative? 2, right? 2. Do we have 2? We do. Okay, so that wasn't too bad, right? Essentially what you're going to do is every function that has a y in it, you're going to multiply by a dy dx from the chain rule. Okay, and now we're done, right? That was exhausting. No, we're not done. We have some algebra left to do. Algebra's fun, right? So we need to collect like terms. We still want to solve for dy dx. There's a term with dy dx, and here's a term with dy dx. Collect like terms. Let's bring it over to the left side, okay? So dy dx is still over here, and he welcomes his new friend, which becomes minus secant of y, tangent of y, or sexy tanny, right? Oh my, times dy dx, and that equals 1. Now, those are not like terms, are they? They're not like terms, so we can't just add them together. But we're trying to solve for dy dx, and both terms do, in fact, have a dy dx in it. So what's the algebraic maneuver from here? What do we do? Yeah, the GCF or F it, I heard, right? We F it. Let's F this thing. Dy dx. Now, don't make this mistake. Whoa. Factoring out is dividing out. Yes, yes? Yes, yes. Guess what goes in the first slot when I factor a dy dx out of itself? A 1. You think I've ever seen anybody leave it blank or put a 0 there? Yes, yes, but not y'all, right? Minus sexy Tanny. I should probably quit saying that. Secant of y, tangent of y. There you go. And then it equals 1. All right, and now we're rounding third. We're heading home. The ball's in the outfield. We're the Astros. We're going to win. Okay. All we have to do to solve for dy dx then is divide both sides by 1 minus sexy Tanny. God, I said I wasn't going to say it anymore. Dy dx equals 1 over 1 minus secant of y times tangent of y. Unbelievable, right? That's it. Now I know what you're saying. You're saying, well, that doesn't look that doesn't have x's and y's in the derivative, right? That just has y's in the derivative. And you're right. Okay. Notice that this function here, although we couldn't solve it for y as a function of x, we could solve it for x as a function of y pretty darn easily, right? X would equal y minus secant of y. So if a function of the form y equals f of x passes the vertical line test, guess what an equation or a function in the form x equals f of y would pass? The horizontal line test. Yeah. So this is still a curve. It's still an equation, but it's not a function of x. Now, is there a way to see what this thing looks like? Yes, I'll show you. Let me see if I can pull it up here. Do a split screen and open up. Well, you can do it with me or not. Open up a Google browser, and I'm gonna type in Wolfram Alpha. Wolfram Alpha. Yeah, X and Y grapher. I don't know how to say it. Grapher. Yeah, we can do split screen now. Thanks. Yeah. Plotting and graphics examples. Let's see. Graph of function, plotting functions and graph. Plot. There we go. There we go. Okay. So here's the plot, right? So I'm over here. I'm going to come in here and I'm going to, whoop. I want us to still plot. Whoa. Whoa. Get back over there. Okay. We can actually, your TI calculator won't do this unless we change the variables and then turn our calculator sideways. But Wolfram Alpha supposedly will. So let's try it. We're going to plot y equals, there's the equal sign, x plus, oh boy, there's a plus sign, secant. We actually spell it out, SEC, like the Southeast Conference, right? Of, and then y, and we close it, okay? And we take a look. Does that look like what we want? Yeah. So I'm going to get rid of the keyboard. And if I hit equals, it should effervesce, right? It should like start bubbling like it's working. Let's see. Effervesce. Oh, I guess they've updated their website to get rid of the effervescing bubbles. It used to look like you open a bottle of Sprite. Hey, there it is. There it is. There's what the graph looks like. Does it pass the horizontal line test? The horizontal line test. Yeah, it does. It does. So notice the reason that the derivative equation only has a y in it is because you don't really need the x value. If you gave me just the y value, I'd be able to pinpoint where it is. All right. Now notice that this function looks like it has vertical tangents, right? It's not a function of x, but it looks like it has vertical tangents, doesn't it? There's one over here. Every time it does like a horizontal about face, there's going to be a vertical tangent there. What's the slope of a vertical line? D&E, because it's some type of infinity, right? So when you have a quotient, that's going to be when the denominator is 0. So if you wanted to know what those y values were, you could set 1 minus sexy tan equal to 0 and solve, okay? 1 minus sexy tan equals 0 and solve. I don't even know if I want to try it out, but let's see. Secant and tangent. If you plugged in an x value like pi thirds, pi thirds would be somewhere in here. You would be able to find the slope of the graph right here. Okay. So there's a lot of curves out there that represent graphs that represent, or curves are graphs that represent real life phenomena, real life behavior. And we want to know how fast they're changing. So there needs to be a way to find the slope of the tangent line when it's not a function of x. Okay. And that's called implicit differentiation. So there you go. How was that one for the first one? What was really our second one? Good. Yeah. Okay. So there's Wolfram alpha. I'm going to keep it open and shrink it. Okay. Let's move on to the next one. All right. Find the slope of the graph, blah, 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 at 1, -3. Okay. Now, I'm going to do this one a couple of ways, or at least talk about it. Our end result is to find a slope at a point, right? A numeric slope. So unlike the previous one where I had the derivative equation, and all I had to do is plug in variables at different values to find the slope repeatedly, in this one, my end result is the numeric answer, slope at a point. So that might inform how you do the problem, okay? So let's go ahead and analyze the equation first of all. We got y cubed plus y squared minus 5y. There's a lot of y's and x's in there. It's not solved for y, is it? Nope. Can we solve it for y? Do you want to try and solve it for y? Ooh, that would be kind of hard, wouldn't it? Now, believe it or not, there is a cubic equation like there is a quadratic equation, but I don't know what it is, and it's very, very long. So I don't think it's worth looking it up on the internet and using it just to take the derivative explicitly when we know how to do it. How? Implicitly. Okay. So let's go ahead and just jump right in. Anyone want to collect the terms first before you take the derivative? Good. Okay. If you want to, you can bring the x squared across. I'm just going to take the derivative of both sides with respect to x, and I'm going to show it by doing that, right? d dx equals? No, d dx colon. Is that dy dx or d dx? D dx. Some people put dy dx colon. No, it's a verb. It's an action word, okay? And now we jump in right away and take the derivative. How many y's do we have? 3. Guess how many dy dx's we're going to have? 3. Now, what would be the derivative of y cubed, do you think, with respect to x? 3y squared times dy dx. Yeah. So really what you think about it as, put little parentheses around it, right? Blob cubed. Blob cubed. So that becomes 3 blob squared times the derivative of the blob with respect to x. What's the derivative of y with respect to x? Well, it's dy dx, okay? So you take the derivative like you normally would. You just have to remember that our independent variable is x. So anything that's not an x gets a d variable dx, okay? Chain rule, times d variable dx. All right, guess what the derivative of, no, don't guess. I'm sorry, my phrasing is all bad. Tell me what the derivative of y squared will be. 2y dy dx. Very good. 2y dy dx. That's kind of fun to say, right? 2y dy dx. 2y dy dx. You can't go trick-or-treating with 2 witches because you don't know which is which. All right, minus, what's the derivative of 5y? 5 times dy dx. Very good. All right, times dy dx. Whew, minus, we cleared the gauntlet of y's. What's the derivative of minus x squared? Negative 2x to the first times the chain rule, wink, wink, dx, which we don't need. Right, good. Equals, all right, equals What's the 0? Right, 0. All right. So that's the calculus step. d dx colon, take the derivative. How many dy dx's do we have? 3. That's how many we're supposed to have, right? Good. So now it's just time for algebra, algebra. Oh, I love some algebra. That's a fantastic sweater. I finally just read it.
Thank you. It's
Yeah.
smart.
Yeah. You know, growing up, I always thought that the restaurant was water burger, like the fluid. And I was, they must have some juicy hamburgers, right? And then, and then I learned it was Whataburger. And then I got it like, oh, what a burger, right? But they're still juicy.
They are.
Yeah, but not as juicy as Wendy's. And that's not because the meat's juicy. At Wendy's, they put like a gallon of mayonnaise on you. And so you need like, can I get a junior bacon cheeseburger and a pound of napkins? Yep. All right. We need to solve for dy dx. So we're going to collect like terms. Hey, look, we already have like terms on the same side, don't we? So guess what we're going to do with the dy dx in each of those terms? F it. Pull it out. F it out, right? So dy dx, parenthesis. We're left with 3y squared in the first term, plus 2y in the second term, minus 5 in the third, equals, and notice what I'm doing in one line. I'm factoring out these highlighted pieces, and then the minus 2x that didn't have a dy dx, guess where I'm taking him? Behind the woodshed, right? No, to the other side. Yeah, yeah. What does that analogy mean? I'm taking him behind the woodshed. Yeah, that usually means we're going to hit him with a piece of wood repeatedly. But anyway, don't do that. Be nice to people. Be nice to people. Do it in front of the woodshed where people can see.
Make a point.
Make a point, right? Set an example. Hey, guess what? We're rounding third, heading home. Ball's in the outfield. Astros are going to win again. We're the Astros. All we got to do is divide by that blob. So here we go. dy dx is going to equal 2x divided by this fantastic blob. There you go. And so now for the first time, we have a derivative equation that requires both x and y, a dual coordinate to find the slope at a point. And that's because my equation up at the top was certainly not a function of x. And notice to solve for x as a function of y, because it's squared, you would need two different equations. So it's not a function of x either. All right. There it is. Now, we didn't answer the question, did we? It said to find the derivative at the point 1, -3. Well, now that we've got the derivative, solve for dy dx for any xy, let's go ahead and plug it in, dy dx on the left, evaluate it at, right? Don't forget the when bar. And then because it's an ordered pair, that's how you do it. Okay, that's how you do it. You just put the ordered pair down there. Simplest way to do it. And then you plug it in. Now make sure you're plugging in the right thing, right? So 2x, that's going to be 2 times 1, that's 2. Y squared is what? 9 times 3, that's 27. That's going to be a -6, -5, right? Free response, we are Brooks and what? Done, right? We're done. I'm not going to simplify. The notation is there. It's perfect, full credit. Multiple choice, I'm going to keep on keeping on, right? So 27 minus 11, that is somewhere in the ballpark of 16. And then 2/16 is equivalent to 1/8. Right. Nice. Nice. 0.125. Pretty shallow slope there, isn't it? Pretty shallow slope. I'm curious what the graph looks like, aren't you? Yeah, real curious. Let's see. Let's see if we can graph this puppy and go to the place on the graph 1, -3. So I'm going to come over here back to Wolfram Alpha and let's see. Well, let me put a new one. There it is. Whoa, come back here, boy. Okay. Why won't it? Okay, hang on. Whoa, I'm getting all kinds of windows now. Input. No, no, I don't want that. Hang on. I got to go back. There we go. I want the plot box. All right. So Just bear with me here. I'm slow with my typing here. Y, you got to use a caret 3, y cubed, and then plus y squared. Now I got to go back to this screen. Oh man, all these different sub menus, right? Y squared, caret 2, minus, now that's over here. Ooh, minus. How am I doing so far? Pretty good? Okay, thank you. Check because again, I don't want a careless mistake and get the wrong graph. So y'all are my second pair of eyes. X and then equals. Let's see, the equal sign is here, and it's -4. Okay, double check, triple check. How does that look? It looks good. Okay, so now, man, I need to write these people and ask them why it doesn't effervesce. It used to have like little bubbles there. All right, there's what the graph looks like. It kind of looks like a uvula, right? Right, a uvula in the back of your throat. Right. All right, let's see. Let's go to the point 1, -3. 1 would be, let's see, 1 would be like right here, and then where it intersects the graph is right down here. Guess what the slope is right there where my finger's at? You're gonna have to imagine at home. It's 1/8. Is that reasonable? Yeah, that's totally reasonable. It's pretty shallow right there. Hey, look at your graph. Where do we have horizontal tangent line? Look at the uvula graph. At what value of x do we have a horizontal tangent line? 0, right? Yeah. It looks like it has y-axis symmetry, and it does. So right down here at the bottom, it should be 0. So when x is 0, do I get a 0 slope? Let's see. Come over here. dy dx, if you plug in a 0 for x, and whatever the y value is, you're going to get 0 over a number. Oh my gosh, it works, right? So implicit differentiation is useful when you have curves that aren't functions of x. They don't pass the vertical line test. Okay, thank you, uvula. You've done great. Now, that is certainly a viable way to do it, but it takes a little bit more work to algebraically solve for dy dx because your terms are unlike terms. So this is where a strategy would come into play. Let's take the derivative now, and then instead of solving algebraically for dy dx and then plugging in, let's plug in and then solve. Now, the derivative is going to be the same. So if you want to just copy this first line right here from up above, or you want to do it again to get extra practice, that's fine. So there's the derivative, yes? If you know that you're not going to need this again for anything else, like it's a multiple choice question, or you're just trying to find the slope for the tangent line, rather than solve for dy dx and then plug in, it's easier to get a numeric slope by plugging in first. Now, when I plug in, there's no dy dx to put the when bar on. So guess what I have to do? I have to still show that I'm plugging in. And here's how you do it. At the point 1, -3, colon. It's not showing up. I'm right here by the hub. At 1, -3. I wrote, oh no. Okay. Go ahead and put at, the at symbol, or at, and then put the ordered pair 1, -3. And then go ahead and plug in. Plug in. I'm going to try and reconnect here. While y'all are doing that, plug in and then solve for dy dx. And I think you'll convince yourself that it's a little bit faster, a little bit niftier. And it's simply because you're going to have like terms. You're going to have dy dx's that have coefficients, all right? So you're not going to have to factor out a dy dx. All right, I'm back in a smaller window, but I don't have time to adjust it. So I'll catch up with y'all. We're going to get 3 times -3 squared is 9. 9 times 3 is 27. So that's just going to be a 27 dy dx. Plus 2 times y, that's actually going to be a -6 dy dx. And then a -5 times 1 is 5. And then that's going to be -2x. That's -2. Oops, I forgot the dy dx. This is what happens when you know that you're running out of time. -2. Okay. So now notice I don't have to factor out the dy dx, do I? Because all of the other symbols when I plugged in became coefficients. So now it's just what's 27 minus 11? 16 dy dx equals, bring the 2 across, and then you get dy dx equals 2/16, which is 1/8. It's the same thing. Oops. Now, the problem with doing it this way is now if you wanted the slope at some other place, you'd have to do all the algebra again, okay? So there's a difference between, are you looking for dy dx, the function, or are you just after a numeric slope? That's a strategy. If you're just after a numeric slope, plug in, then solve. But when you plug in, you got to indicate what you're doing, okay? Anytime you go from a variable, oh, thank you. Happy Valentine's to you too, Mason. Anytime you plug in, you go from a variable to a constant, you need to indicate how you're doing that. All right. Implicit differentiation, kind of fun, right? Yeah, emphasis on fun. Y'all